intro into satellite QKD, which is kind of the second half of the implementation of QKD that we heard about yesterday from Eleni. So I'd like to give a bit of I'd like to motivate the question, why satellites, right? And why are we even doing this? And so it's about this for communication, right? To make QKD really viable and useful, we have to tackle the problem of covering, in the end, global distances. And if we go across a continent or even across an ocean, there's like thousands and thousands of kilometers to be covered, and it's going to be difficult. And in particular, one problem is that ground-based channels, and we'll talk a little bit more about that in a moment, generally, unless we have quantum repeaters, which are still a big topic in research, but haven't really made, haven't been deployed in any way, the losses scale exponentially with the distance, roughly speaking, right? So that's what you can remember, because the losses per unit length are always equal. The probability of losing a photon is equal per unit length. So if you integrate over that, it turns out exponentially, so it's an exponential drop of signal. While a satellite channel actually scales quadratic with the distance. So for shorter distances, that doesn't really matter too much. But once we're talking about 1,000 kilometers and beyond, then the exponential scaling really kills any kind of signal, and it becomes very difficult. And so that's ultimately why satellite quantum communication, satellite QKD is a topic. So this has been known for a while, and here's a sort of one summary which comes from this overview paper from 2021, and it's in no way comprehensive, but here's a bit of a list or an overview of some major milestones and missions. They started in this paper, I'm technically a part of that paper, it kind of arbitrarily started in 2005, but actually it began way earlier, the work on satellite QKD. But here are some of the major milestones where the Chinese group demonstrated a free space quantum communication with their with the satellite payload hardware right on the ground, and so on. And what are the big major milestones in terms of satellite QKD? And we'll talk more about it. The satellite Mitzius mission was launched in 2016 and showed a lot of groundbreaking results and progress on that on QKD between space and ground, and like I say, we'll talk a bit more about that a bit later. Other notable things are just actually last week, the first German CubeSat with quantum technologies was launched, and actually some colleagues here from the Munich group could say more about that. But it just went up. And I would also like to mention in Canada, we have the KeySat mission, and I'll say a little bit more about that as well. That's the mission that I initiated and I'm now leading in Canada, which will hopefully launch about a year from now, the autumn of next year. So, the other reason I wanted to show this is that while the ideas have been around, and it goes back to 1995 and other studies in the year 2000, the ideas have been around for quite a long time. There was quite a bit of time of not really much happening until missions were launched, like the Chinese mission, or like in those red boxes, missions that are under development or about to be launched, or like the German one, Cube, which was just launched very recently. And now this is not even comprehensive. There's many more missions actually in the works for demonstrating satellite QKD. And actually, next month, a project will launch. It's a US project to put an entangled photon source on the ISS and test photonic integrated source in the space environment, and actually my group from Canada, we were also involved in that project that delivered detector systems. So like I say, there's a lot happening. So now to get back to the question of why satellite QKD, I'd just like to briefly take a step back and just look at some of the prerequisites for a QKD system, for implementing a QKD system, because that will help see what some of those technical trade-offs that have to be done and technical choices, how they can be decided. And my goal is that I'm aware that there's a lot of people from various directions, and only some are from physics, and even and a subset of those are actually from experimental physics. So I'm aware that a lot of these details might be a bit much to cover, but I'll try to give you a sense of where things are, so you can have an idea of how this works. So first of all, the first question is, how do we encode the quantum information onto photons? So if we're using a photonic channel, which is actually still one of the best quantum channels because it is very fast. Photons travel at the speed of light. Photons are also very good. They don't couple well with the environment, so they have pretty low, let's say, coupling to environment, meaning good decoherence properties. And there's multiple ways to encode quantum information. And what you can remember is that practically all degrees of freedom of photons can be used or have been used for quantum information. So the one that is maybe the most widely studied for QKD is like polarization, horizontal, vertical, for example. But then there's time bin, where we have two different times. Sorry, the screen, whenever I touch it, it changes brightness. The early late time bins, right? They can be used for quantum information, and one can use protocols like differential phase shifting and so on. Frequency bins and frequency sidebands have been used for encoding information. Here's an example of an experiment where they had entangled photons with entangled in wavelengths. Another big one that's been studied a lot is spatial mode. Most simply, actually, an interferometer with two distinct paths can be seen as a qubit. Was also brought up yesterday by Eleni that the kind of dual rail representation is a qubit, right? The photon is either here or there. For communication, maybe more interesting is spatial modes. However, for satellites, that's not really viable because of the large distance. And then finally, there's also the quadratures of light, where the information is coded into the quadratures like X and P and so on, and of course can also be used for quantum information. And but I'll say right away, for satellite links, there's various reasons for that, but ultimately polarization is the preferred choice because it's easy to use and implement. Also, atmosphere practically has no impact on the optical polarization. But there are problems with building the systems, and which we learned the hard way with our payload systems. So there's pros and cons, but still it's typically the preferred choice. But I will say there have been studies on time bin in free space, frequency bin, spatial mode in free space, but also CV QKD in free space, and also with satellites has been studied and proposed. And so all of that is possible. But I will say the one that is the most established and proven as well is the polarization. And then another prerequisite for any QKD system actually, but in particular for satellites, which is harder to implement, is the synchronization. And I know this is a very technical, experimental challenge, but it's important to get a sense of what's going on. So if Alice, we have our Alice, which wants to send, one photon after the other. And if we're running, let's say, at 500 megahertz, that means every 2 nanoseconds we have a pulse coming out of Alice, right? And Bob has a detector, or detectors, to analyze the photons. And this might be, 500,000 kilometers. So you can imagine there's a lot of signal pulses traveling. And then in order that Alice and Bob can find the events that belong together, they have to do what's called a coincidence analysis or a time correlation. They have to look into a window that is less than this pulse separation, so less than the 2 nanoseconds, in order to identify which of Bob's detection event belongs to which source event at Alice's side, right? Which they have to identify them and bring them together. Otherwise, the whole protocol fails, right? Because every event is, of course, a randomly encoded signal. And the way they do that is they have to have clocks. So both Alice and Bob have clocks, which have to be very stable. And then they will record times. Alice records times of emission. Bob will record times of detection. And you somehow have to bring that data together and do a correlation, a time correlation, which is called sifting, right? And this is what leads to the sifted key in the end. So the sifted key ends up just being a sequence of zeros and ones in the end, or maybe a bit more information. There might be basis information. But all of those technical details in the background have already happened, right? So the time analysis, the time correlation. And they use various ways to do that. They will have stable clocks, sometimes even atomic clocks, like small rubidium clocks. One can use positioning information from, let's say, for example, GPS. One can send additional pulses or signals back and forth. And ultimately, the quantum signal itself is used as well for clock recovery, so that Bob can fine-tune his timing based on Alice's photons that appear every once in a while. And here's an example of some data from this experiment at Tenerife with 144 kilometer distance. And the photon arrivals, so this is nanoseconds, and the photon arrivals were then in the end compensated and corrected so that the correlation was of these photons was in a very narrow timing window. So for satellites, that's quite a tricky problem because the distance between the sun and ground is not stable. It's not like a fiber optic. In a fiber optic link, the drift is relative. There is some drift due to temperature of the fiber and so on, but it's not as much. The satellite can vary within minutes. It will vary, hundreds or thousands of kilometers, come closer as it's passing overhead, and then move away again. So that poses a major challenge in any such system. And then, so now let's briefly look at the 2 quantum channels that we have available. That's another important prerequisite of any system. And for photons, we have 2 channels available, free space or fiber optic, right? Those are the 2 options. And I won't say much about fiber optics, but just to illustrate the challenge of distance. So this is I'd like to discuss the absorption just briefly. Here we have photon wavelength. So 1 micrometer is here. And this is the absorption measured in decibel per kilometer. And so the lower this number is, the less decibel per kilometer, the better. And what we can see is that there's, in general, this glass medium, so fiber optic means it's just a long piece of glass that has been stretched out. The photons are traveling in this glass all the way, and there is an absorption minimum here at 1550 nanometer, and the best fibers have on the order of 0.16 dB per kilometer, and that is actually the minimum of that glass medium. So there's no way, that's fundamental, there's no way around that. for this particular class. So this also shows why telecom is all at 1550 nanometer, right? It's because of this absorption minimum. There's some other notable ones. Here's another sort of a local minimum at 1310. That's the dispersion minimum, which is interesting for telecom. And just for reference, 800 nanometer is here, where there's on the order of 1.5 dB per kilometer. And 800 nanometers is interesting because a lot of earlier quantum optics sources and so on, and also for detectors it's good, have been at that wavelength. Now, just to illustrate the problem, if we want to send photons over 100 kilometer, just for reference, at 1550 the transmission is, let's say 3% roughly. 1310 is 0.1%, so it's not so good, but it's would still be okay for most systems. However, 800 nanometer, it suddenly becomes a really high number, right? It's just this exponential scaling which breaks down the rate, so the photon rate really drops. And this goes back to my earlier point of why satellites, right? Okay, I have this absorption at 1550. So even if we use 1550 on the ground in fiber, a few hundred kilometers is possible, and the longest direct transmissions are on the order of 400 kilometers. But those kind of systems are more like demonstration QKD systems. They are hardly at reaching a rate that is, so it's difficult to do any finite size key, for example, so it's more like proof of principle. So the commercial systems one can buy today are usually in that area of 100 kilometer, maybe a bit more, but that's roughly what they can do. And so to go beyond these few hundred kilometers, that's where satellites are needed. So for the free space link, on the other hand, there is things are different. If I now don't worry for a moment about absorption in the atmosphere, if I just think of an optical beam, so let's say I have a telescope, I'm sending an optical, like a laser beam, then the only kind of loss mechanism that I will have is that the beam will naturally widen out, right? So there's for example, a concept of a Gaussian beam, where I have a certain beam waist where it's as narrow as possible, and from there onwards the beam will just naturally diverge. This is fundamental, and the angle of divergence relates to the wavelength and the beam diameter. 2 times omega 0 is this beam diameter, right? But what you can see is that this divergence angle will be, so it depends on essentially the wavelength and the diameter. So the shorter the wavelengths, the smaller the angle is. You're going to have a small angle to get a long straight beam. But also the larger the diameter is, it will also reduce this divergence angle. That's why ultimately one has to use larger telescopes for sending and receiving those kind of optical signals or optical beams over a distance. And so the loss mechanism is the following. So if I have a transmitter with a certain diameter and I'm sending the signal, the beam will grow and spread out. And at my receiver, I will have a certain diameter, but then the spot might already be larger or will be larger than my receiver. So then literally a lot of photons will just pass the receiver and pass on, right? And so they're not captured. So only a small fraction is captured. So roughly the area of the receiver aperture relative to the spot size area will give us the transmission loss. And here's the more official equation for that, the so-called optical antenna gain. This is for a Gaussian beam collected into a circular aperture, but we can we can look at this version of this equation if we are like in the far field, so we are very far away, and the spot has grown to be much larger than the receiver. So then the transmittance or the efficiency of this link will be the product of this is the diameter of the transmitter, the diameter of the receiver, divided by the distance, z and lambda, and all of that squared. Lambda is the wavelength of the light. And roughly speaking, this is the transmittance, right? And so now, yeah, as you can see, right, also this equation tells us the larger the two telescopes are, the transmitter and receiver telescope, the better my link will get, right? So that's roughly the main idea. And so this is already the core point why we even do satellite QKD, and why it's also being pursued by so many different groups, as you can see in this overview map. Okay, are there any questions so far on the motivation and concept? Yeah.
About fibers, what about hollow core fibers? What does it change?
Yeah, that's a very good question. Fiber technology, right? So the graph that I showed is for standard solid glass fiber. It's essentially fused silica. Yes, there's lots of alternate fiber technologies like hollow core fibers or other media. There's so-called heavy metal doped fibers, I forget the exact terminology, which in principle could be orders of magnitude better even, right? But it's the manufacturing. So all those fibers, while in principle they could be much better in terms of losses, to get a manufacturing of a long stretch of fiber, we're talking maybe 1,000 kilometers, which has very little irregularities on the way, both in the medium or in the let's say hollow core, geometry. This is the problem, the manufacturing. So they cannot manufacture the tolerances that are needed to reach those hypothetical limits. But yes, you bring up a really good point. I was once at a NASA workshop, this was several years ago, about blue sky research in space. And they invited me to talk about satellite quantum comm. And I was presenting my stuff, right? And then I brought up this point about fibers, right? Fiber technology. If we find better fibers, we could do 1,000 more kilometers on the ground. And then one guy stood up. Yeah, he would rather. He said, yeah, you should develop fibers rather than spending those millions into a satellite system. Just work on better fibers. So, but I think it's not that easy because. Of course, all of the telecom industry would also want those better fibers. So if it was that easy, it would already be moving forward. So, but yes, for someone interested in research directions and you want to go into fiber technology, there is potential. There are materials out there which are substantially better in principle. Yeah.
I want to ask about the time synchronization. Okay, better clocks and everything, but it also is influenced by the environmental condition, weather and everything, how this is handled. I mean, the shifting will be changed over time.
Yeah, no, it's so the question was about the shifting and how does it change? Yeah, it depends on a lot of things, and the challenge is to make algorithms and procedures which can handle any kind of variation and drift, and in particular the satellite link is special also because not only do your Alice and Bob systems drift, right? All clocks drift, by the way, but also your channel is just drifting. And so the drifting channel, you have to account for that because, I mean, drifting, it's the distance of the satellite to the other station is not constant, right? The satellites are flying very fast. And low Earth orbit satellites, you can have 20 microseconds per second easily of change of time of flight, which means if the pulses are 1 nanosecond or less, and you've got 20 microsecond variation per second, so your algorithms really have to be good. So, and the way it's done is usually by having a multitude of methods, like I mentioned, position and other things, to combine them and realize a good synchronization algorithm. So now, however, unfortunately, we do have atmosphere. Unfortunately for satellite QKD people. When sending optical signals to a satellite or from a satellite, we have to account for atmosphere. And this is a sort of a generic transmittance of a vertical beam going from ground to space. And it's actually, but still, it's quite, quite moderate. So we're talking at 800 nanometer, around 50%. Generally, there's this Rayleigh scattering, which is a general fundamental limit. And in between, you can see lots of resonances from either molecular gases or like aerosols, water vapor, and those kind of things. They all cause various resonances to happen. But what we can see is that some of the typical wavelengths used by laser systems are actually okay. So 1550, interestingly, here, is actually pretty good in terms of transmittance in the atmosphere. And there's also no actual resonances. 1064 is not bad. Around 800, 850 is quite good. 785. This one is also quite good. 670. And even down to green and blue, it can be okay, right? So it turns out, by the way, interesting fact, and we won't go into details, but if you look at this curve, right, it says the transmittance is lower at shorter wavelengths. If one now combines that with the transmittance of these telescopes that I mentioned, it has an opposite effect, because the way the wavelength comes in, it's actually, for the same size of telescopes, the shorter the wavelengths, the better. So roughly, it's not perfectly canceling, but roughly those two effects cancel. So I was actually surprised. We did a comprehensive analysis about all of this. You can see it in this paper. It's more than 10 years ago. I was actually really surprised, because we studied QKD with all those wavelengths and modeled, years worth of satellite passes and all kind of things. And in the end, they came out to be quite similar, right? They're all in the same order of magnitude of QKD rates. I was actually surprised. I was expecting there would be a clear winner and everything else is, you can forget about, but it wasn't the case. Which is also, in a way, unfortunate, because now it means the choice of wavelengths in some way depends on many other things, last one being cost. So a lot of technical and system considerations actually come in when deciding which wavelengths to use. So how do we actually generate photons that are going to be used? And I won't say much about it. I just want to draw attention to one item, is how do we characterize the single photon quality or single photon nest of a source? And it's done with the so-called second order correlation, G2, and which essentially looks at what is if you have a pulse come out, what is the probability of getting 2 or more photons in that pulse? And as we heard yesterday from Melanie so nicely, there is the problem with the multi-photon clicks coming out of a laser pulse, which can be used for the number splitting attack, the photon number splitting attack. So that's where this G2 can be used to characterize a source. And a single photon source, such as the original BB84 source, would actually have a G2 of 0, meaning at 0 time, it means I just have only one photon, and the chance of getting 2 or more is very low, is almost 0. So here's an overview of the type of sources that can be used for photons. I took this from a review paper from 2011. I mean, it's quite a while back, but it's still the general idea is good. So the first one is faint laser. That was already discussed yesterday, right? We take a laser pulse, attenuate it, and that can be used to implement a QKD source. Has its problems. And then the other ones that I used is just to highlight them. So roughly speaking, PDC, what's called PDC, that's parametric down conversion, where essentially one photon from a laser can be converted into a pair of photons, and that creates entangled photons. And there's a lot of different variants of that, but generally speaking, that's a straightforward method to produce entangled photons. That's also widely used for QKD. It has benefits that the entanglement doesn't suffer from the photon number splitting attack in the same way. It also provides randomness. So there's some advantages of using entangled photons in a QKD system. And the other type of sources that I used are based on single photon emitters, where there's many different technologies, quantum dot being one of them, and that can also be a very interesting direction. Again, because those single quantum emitters don't have the number splitting attack, right? That's why it's used. And in free space or satellite QKD, quite often a method of choice is to have multiple lasers. Here's an example from the Los Alamos group. Richard Hughes led the group in around the 2000s, which did the early concepts actually of satellite QKD. They had a source based on 4 laser diodes, right? Which are they are combined with a set of beam splitters. So each laser has a different polarization state, and they're combined and output to the exit aperture. And then when Alice wants to send a certain pulse, she then just has to decide which laser to pulse. An important feature is that actually this source can only be considered secure if it has a monitor at the output, meaning a fraction of the signal has to be picked off at the exit, and that has to be used to verify that the pulse intensity is really secure. So it has to be less than a photon per pulse. Otherwise, the number splitting attack would just make it all unsecure. There's several things to say. Decoy state was already mentioned. That's really important. And the other thing to mention is that another type of QKD source is to have one laser and fast modulators, which has some advantages, because a problem here is that all of those lasers can have slightly different properties like wavelengths and pulse shape, and they can all create side channels. So the one laser with fast modulators can be better, but I am not aware of such a source in a space system. I know people have developed it and are working on it, so usually it's of this kind, where we have multiple lasers that are combined into one. And another technology, I'm sorry, I'm going fast over all those kind of aspects, but I want to give you a sense of the kind of trade-offs and headaches we have to deal with when we're looking at a satellite QKD system or any QKD system. Photon detectors is another thing, right, to worry about in your QKD system. Here's an overview. This is a review, even a little earlier, from 2009, than the source review of photon detection, single photon detection techniques or technologies. And all of them have different properties and different parameters, but I'll just highlight a few that are mostly used for QKD. The silicon APDs are used a lot. They are great, they have very good properties. However, they don't work at telecom. Because silicon band gap can only reach to just a bit more than 1,000 nanometer. and longer wavelengths than 1,000 nanometer silicon is actually becomes transparent. So telecom photons would just, they wouldn't even see the crystal. They would just pass through. So one has to use, for telecom, one has to use materials like indium gallium arsenide, APDs, which they work, but they are far less quality than the silicon detectors. So there's a lot of problems. So here's just a really quick overview and some pictures of commercial devices. Like silicon APDs, they are great. Here's a picture of a silicon detector module, and here's a chip. And in our Canadian satellite, actually, we have those kind of devices on board for detecting the photons. So they have really good properties. And if we need telecom, one can get detector modules. So it's actually no longer in production. This is a module from ID Quantique, which has an in-gas photodiode. It does, they do work, they're good, but they're not as good in terms of efficiency and after pulsing. So lots of problems. And the gold standard for detectors is essentially superconducting nanowires. I will tell, so just so you know, these are the best possible detectors one can have. High efficiency, they work really well. Yeah?
How much do they cost?
All of these? Yeah. So these ones are really expensive. You would pay $150,000, $200,000 for a system. The main cost driver for the nanowires is unfortunately the cryo system. And so all of them have pros and cons. These ones are relatively low cost. A device like that you can buy, even you can get it on DigiKey. $1,000 maybe for a device, maybe cheaper, But then you have to build your own electronics, which isn't that difficult. And these ones are in-gas are maybe sort of in the middle, $20,000, $30,000. So just to give you a sort of a price range. This also brings up one problem. The one disadvantage the nanowires have is they need cryogenics. They need to be at a few Kelvin to work. You need cryogenic systems to operate them, and that is just really difficult. So putting them into space is possible, but it's very expensive. Would require a huge satellite. But even using them in the ground has challenges because at the ground station, let's say receiving signals, because they are usually single mode fiber coupled. And so if you have a beam coming through a telescope, coupling it to single mode fiber is actually very inefficient. Without adaptive optics. So it brings up complexity. So there's a lot of pros and cons to consider. So, and that brings me to actual satellite QKD systems. So there's a lot of system trade-offs that have to be considered for such a QKD system. And I was trying to give you like a quick sense of what's out there. So you have to think about what kind of source do I want to use, right? What kind of detectors? Channel, obviously that's the satellite or free space. But then I have to wonder, what kind of distance are we talking about? How high will my satellite be? Topology and ultimately the cost will matter, right? For a satellite mission in particular, like a big satellite with 2 telescopes for an entangled source, it will cost way more than a small CubeSat that has a small transmitter on it, right? So, and we're talking, hundreds of, it can be up to hundreds of millions of dollars, right? So one has to make those design choices carefully, and in particular, wavelength is a big question that starts off, and then size, power, weight is called SWOT, right? What is my source and my detectors? What kind of size, power, weight considerations do I have, right? And so but to sum it all up, all that I've said up to now, right, in this summary of components and so on, I like to summarize in this way. So here's my wavelength spectrum that we use for QKD, right, from 1550, let's say up to 400, so that's UV. So let's say that's our spectrum that we can consider. And roughly speaking, we have the following sort of trade-offs to think about. Detection can be really good in this region, 400 to, let's say, roughly 1,000. That's when I can use silicon APDs. But if I go longer, detection will be a challenge. Beam diffraction, this kind of loss mechanism of beam, spreading, is better the shorter the wavelength. And if you remember that equation, the shorter wavelengths, the lower the wavelengths, the better. On the other hand, the absorption in the atmosphere, as we see in this graph, is better the longer the wavelength. And then finally, if I think of sources and lasers for like down conversion or weak coherent pulses, generally speaking, the longer the wavelength, the easier it gets, typically, right? And the shorter the wavelengths, the more tricky it can be. So, and all of this together, like I was trying to say earlier, there's no real winner, right? One has to then make a choice of all those considerations, and there's actually more considerations to bring in, which lead to such a system. Okay, so any questions up to now? Because now I will go into looking at actual satellite examples of satellite systems. So, so what I'd like to show you is just a few slides from a paper from the Chinese mission, the Meteos mission. In particular, the satellite to ground QKD experiment that they performed. It was published in 2017, and so that will give you a sense of what this looked like, and also I have a slide or two on the concept and the performance. So what they have is a source on board of the satellite, sending the QKD signals to the receiver on the ground, at the ground station. And they already indicated the photons as those little red dots. So the way they did it is they have actually 8 laser diodes. And they're all polarized differently and combined. It's 850 nanometers. And this is then sent through the transmitting optics. Any thoughts why we have 8 lasers, not 4? Does anyone have suggestions? Yeah.
I think you mentioned different lasers are being used.
Yeah. So if they do BB84, they have, yeah.
Decoy states maybe?
Decoy states, yeah. So they have 4 lasers. 4 polarizations, but they need the different intensities. And so they would choose 8 lasers, and they're tuned differently so that they can still operate well, but have different amplitudes. And then it passes through some optics, ultimately sent through a telescope of, I forget the exact aperture, like 15 centimeter in that kind of range. This is then the downlink beam. They also overlay a laser, 532 nanometer, which is green, sent to the ground as just as a beacon laser. So the ground station, in order to find the satellite and really track precisely, it needs a laser coming down, it's called a beacon laser as a guidance. And that's what this green laser is for. And on the receiver side, they have a telescope on the order of 1 meter diameter, which picks up the signals, and then it is sent through some correction wave plates and finally analyzed in 4 detectors, 2 of them in the horizontal vertical direction and 2 more in the diagonal polarization direction. So that's the kind of the BB84 receiver, and so then they record the timings of those single photon detectors. So, right, and already pointed out, it's 850 nanometers. So that means the detection on the ground is also convenient. They can use those silicon avalanche diodes and perform the QKD. They record the timestamps on the ground. They have electronics which can record very precisely what those times of arrival are, and the source is running on its own clock, and then from time correlation, we will then find out which event goes to which source event goes to which detector event. Yeah, like I say, this telescope, I think they had different stations. They were all on the order of 1 meter diameter. What you can see here is a camera which picks up the green beacon light. They also had a laser going out, the 671 nanometer, which was sent upwards, which the satellite optics was using to also steer its beam. And I actually don't have it here, but there's some nice photos where they can actually see the satellite on the camera. They can see the red and the green beams going up and down. And I haven't seen it myself, but anecdotally I've heard from people that beside the ground station, you can actually, once it's locked and once they're locked on each other, you can actually see the green light coming down with a bare eye. So another thing to talk about is the concept of operation with such a satellite QKD. So let's say, so here's the Earth. There's a station, and the satellite, well, let's say, comes. So it starts it's on its orbit around the Earth at a certain altitude. It will start appearing here, and at some point, if this is the horizon locally, it will appear above the horizon. And then, so here they indicated 5 degrees or higher. And so that's where the ground and the satellite will start, they send their lasers at each other, and they will start to try to find each other, right, on their respective cameras. And so there will be a phase where they start to capture the other laser beam and lock onto each other. And by the time they reach the point D, which they indicated here, they will then have lock established, so meaning both sides have successfully locked onto each other. And that means the photons sent by the transmitter can actually be detected at the receiver. So for the continuation of the orbit, they will just keep receiving those photons and the signals, and until the satellite disappears somehow on the horizon. Of course, one challenge will be, this assumes we have line of sight, right? So if you have obstacles like clouds, there might be gaps in this whole link. So, which also directly shows one of the disadvantages of satellite QKD, right? It is weather dependent, right? It is a line of sight operation. So, and all of this for a low Earth orbit satellite, which is at like around 500 kilometers, such as the Meteos, this is just a few minutes, right? So we're talking at most maybe 5 minutes for a full pass, but the ones, so the higher they get, the longer. But the ones that really go high, it's a few minutes, and the actual good link is even less. So because the lower the satellite is on the horizon, the more the distance will be, and also the more atmosphere is passed. So the link actually gets less good. The transmittance drops, and so ultimately it's just on the order of 100 or let's say 200 seconds which are useful. So here we see some measured performance from that paper, and you can see the time now, right, which they took out. This is like 250 seconds. Something like that, and around the highest point of the satellite. Here we see the distance. So we're talking, when they first get the link going, it's close to 1,200 kilometers away. So the satellite to ground. It comes closer, 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 and at the highest point it's the closest, and then gets further away again. Then during that duration, they had the photons, and they sifted the key, and they got on the order of, so this is kilobits per second. On the sides, it's quite low. It comes up, right? Because as the satellite gets closer, the link gets better. And we're talking 10 to 15 say kilobit of sifted key per second. And here we see the Q-bar. It's on the order of down to 1% at the best phase. And what they also showed is this time correlation, which I tried to point out earlier already, where they, despite this huge variation of this time of flight, they have algorithms so they can do a time correlation on the order of sub-nanosecond. So I have 1.2 nanoseconds. But it's actually, I think they got better in the end with better algorithms. So there's quite a lot of processing in here to make this happen. And so ultimately, for this example, they had 3.5 million detected events for the entirety of the path. The average Q-bar was 1.1%. And from that, they were able to generate on the order of 300,000 secure bits after error correction and price amplification. So at least that's what they have in the paper. So that gives you a sense of what of how this looks like. I'm hoping and of some of the way this works and the performance. So one problem right away is you can see, well, we have all this excitement of building a satellite and it finally appears on the horizon, and you might have one such measurement per night. By the way, it's all done at night time because of the background light. And so you would get something like 300,000 secure bits for a good pass. But we're only talking of 100, 200 seconds of contact per whatever, 24 hours or something like that, right? So it's got a limited duty cycle. But of course, it was still useful. They demonstrated lots of different experiments with this. In particular, they demonstrated a intercontinental QKD between a station in China and Austria, and where they used the satellite as a trusted node so that it could generate, at different times, it would generate keys to the two different ground stations. And by combining those keys on board the satellite, one can effectively create a joint key between those distant locations, right? And this shows us that the satellite can be used as a flying trusted node in space, which essentially gives global coverage, right? Because, of course, depending on the orbit, but a polar orbit like we have here in this example, it will constantly go over South and North Pole all the time, and the plane of the orbit is moving with the sun. So if you just wait long enough, it will pass over any location on the ground, right? So you could get global coverage, but of course, remember this is a trusted node, so the satellite has to be secure, right? You have to make sure that if that key information on the satellite has to be protected. The Meteos mission did several experiments. They also had an entangled photon source. I don't have pictures for that, but you can read a lot about that. They had an entangled photon source. They sent the 2 photons to different ground stations, and they achieved what is still the record for entanglement distribution of 1,200 kilometers. And they also used that for QKD, but as well as fundamental bell tests. Yeah. So maybe any questions at this point? Yeah.
So we've talked about orbiting satellites. What about geostationary ones?
This one is orbiting. Well, they're all orbiting, but this one was low Earth orbit, meaning it's on the order of 500 kilometers. Geostationary is a big question, comes up a lot. Geostationary is like 36,000 kilometer high. So the problem is, geostationary is so if this is the Earth, radius of the Earth, right? So the satellite like Meteos and many of the other missions are so-called LEO, low Earth orbit. They are like, you know, we're talking around 500 kilometer altitude. And so one, it passes over pretty fast, and some of you might have seen satellites like the International Space Station and others. They're actually really fast, right? And but with 500 kilometer, the link quality is also manageable, as you can see in those in that data that they showed. If one goes to GEO, and we have this 36,000 kilometer. Benefit is it's stationary, so you have all night to measure. It's not moving, right? But this distance is the killer. The problem is one needs really big telescopes on the satellite and the ground to get a useful rate. I know it's been studied in so we did studies many places in Europe. There was a project for a long time to study entangled photons from geostationary satellites, and I'm aware that in China they're looking at that as well. But it's a major undertaking. Has lots of benefits conceptually, but MEO satellite is another option. Let's say around 20,000. They move slower, and they're not quite as high, and so that's a sort of an intermediate area which could be of interest. But also the size of telescopes is a real challenge. So we looked at, for example, we're in a project called Hyperspace, which is between European and Canadian partners. We were trying to do, what is the link between Canada and Europe from a satellite, and we're right now working on the details of such a mission proposal and in that consortium. And when starting it, I thought, we'll just put in some numbers and get some slightly bigger telescopes, and we won't go that high, MEO somewhere. But it turned out the numbers, they are not. It's okay, but it's not straightforward. So a way out is actually to use satellite flotillas. Actually, to have one way out is to use satellites like one here, and then another one here, and another one there. Right? So having, for example, 3 satellites could be a way to accomplish larger scale networks. Sorry, sorry, I didn't want to go too far off topic. So, but it's an important question. Okay. Yeah.
Mine's unrelated to QKD, but about tracking, because you mentioned clouds. So what happens while you are doing your QKD pass? Because you need to continue tracking to have that lock. What if clouds come in the way, and because you use visible light, you won't be able to track? Will you just use GPS to continue pointing in roughly the right area, then lock tracking again when clouds leave?
Yeah. If right. So normally the systems will keep trying to track. So so when they initially lock onto try to find each other, they use the relative position and timing, right? When the satellite should be where, and this can continue. So if you lose the link in between, the idea is to keep go back to this kind of finding or link acquisition cycle, so that hopefully when the cloud is over, the link can come back. Okay. But I will also say, for example, in our development, in our satellite, GSAT, I brought up that question, and the industry partner working on that, they weren't too sure what will happen with the. They didn't. I think they will try to get it back, their tracking system, but they didn't want to guarantee it. They didn't want to give a guarantee.
Thank you.
But yes, it is a problem. Obstacles come in the way. If you use visible lasers, airplanes, it's a big problem too. You have to watch out for aircraft, and if you get too close with your beam to an aircraft, you have to shut down your lasers. That can be another challenge, in particular if you're like close to an urban area, like to a city and so on. Okay. Sorry. Yeah.
Ever thought about using drones on drone network instead of?
Yeah, drones. Yeah. That is also being studied. There's several experiments on drones. Usually the problem is the size and weight of these QKD systems. People have developed drone QKD, but it's still suffering from the size and weight problem for, let's say, smaller drones, right? If you just have the big enough drone, then it's also fine. We did an experiment with an airplane, and actually we were using the satellite payload prototype that we had, and still our total system was 90 kilograms, right? Just putting everything together. So sizing it, making it smaller is a challenge, yeah. So that would be, it's more about using integrated or micro optics and electronics as well has to be really made more compact and smaller. But yes, there's been a few experiments already on shorter range drone QKD.
What about balloons?
Balloons as well. Actually, balloons, high altitude platform balloons, stratospheric balloons is a really hot topic now. They can be actually big and they can carry larger payloads, but it's because it's this boundary of between atmosphere and space, and up there the transmission quality can be really good with balloons. And they're typically above the weather, so they have less weather problem up there. So there was another question, yeah.
Yes, I was wondering, do you face any restrictions on the wavelength regarding some strange regulations or laws or something?
Not really, no, not from, except aircraft safety. But they care more about the power. How bright is it, right? Because of the blinding of pilots at night. But I know astronomers would like to restrict lasercom satellites. I've heard that, and in particular, let's say, if you think of the Starlink system from SpaceX, they have like thousands of laser links in space. They have hundreds of satellites, and every satellite has multiple lasercom terminals. So they're between the satellites, they're constantly communicating with laser. And so not only have they many satellites which mess up the astronomy, but potentially the laser terminals in space could be an issue, and astronomers don't like that. However, I am not aware of any sort of real restrictions unless you are close to an actual astronomical site. They might if you then start shooting lasers on the ground, I'm sure they would have their local restrictions. Yeah.
They influence also the quantum communication.
No. Yeah. And also the laser between the satellites, I think, is not a big problem because there's no scattering in space. So I'm just saying there's lots of lasers already shooting around in space, which could potentially at some point create problems. And just very quickly, I wanted to show you the KeySat mission, which we're building in Canada. It will hopefully launch next year, a year from now, fall 25. It's a bigger satellite. It's roughly 120 kilograms, a microsat. It's got two features. It's going to be a quantum receiver as well as a quantum transmitter. The transmitter is a small laser source with 4 lasers in this case. And the quantum receiver, though, is kind of the primary payload. It's a larger telescope. This is a 25 centimeter telescope. And it has a photon analyzer and photon detectors on board. And the idea is that with that technology, we can we can test out different sources on the ground. That was the intention, to maximize sort of the scientific value of the mission. We can test different sources, laser and entangled, but also memories, maybe quantum memories or quantum dots, and then do more science. And it was meant to be a quick and lower cost mission when it was proposed, like in 2009, but yeah, here we are. It's still in manufacturing, but it's finished. The system is built and it's now undergoing final integration and testing, so it will be launched next year. But I will say, in my lab, we worked, a lot over the past years on building the mission, like mission science itself, concept, like performance analysis, but also building hardware. So showing that we can take the systems that we had in the lab, just built from regular components and electronics, and turn it into space-suitable versions. So here we have photon detectors and also a data acquisition module built in space electronics. This is our fine pointing system and polarization analyzer built space-suitable. The telescope is just a commercial one, but the tracking system, and all of that was then integrated onto an aircraft. As I mentioned, the Twin Otter aircraft. Here's the optical system, and then this was the electronic rack with our payload electronics. But it also had support, lots of support electronics that were needed, and we were able to test it. Another big problem with space is the radiation environment. So any components in space will experience a harsh environment, which is it's not only the vacuum and the temperature, but it's also radiation. There's a lot of radiation of particles from the sun in particular, and most importantly, unfortunately, the photon detectors, they suffer really badly. It's due to displacement damage in the silicon. So we have silicon APDs, where the protons come in and they can create little defects in the silicon structure. So it still works and everything. However, the dark current increases a lot due to those defects, and that causes dark current in a photon detector, causes more dark counts. And we did multiple test runs. Here's at an accelerator in Canada. It's called Triumph. Here's a picture of the radiation room where the protons come out of there's a big concrete wall, right? Like meters and meters of concrete, and there's a little hole where the protons come out. And then in this cooler box, we had our detector module, which was cooled, and then we exposed the detectors to the radiation corresponding to a certain time in orbit. And what we see is the dark counts shoot up, and then we do some annealing. We did thermal annealing, but also there's methods like laser annealing which can be done, and that reduces the dark counts again. Then they shoot up, then we anneal. So there's a bit of a cycle going on here, but one can show that the dark counts can still be kept in a useful regime. Ultimately, this corresponds to several years in space, and thus we can operate the system. Here you see a picture of the detector module that was built for space, tested in a vacuum chamber actually. So there's a lot of technical challenges that have to be worked on, and the space radiation being one of them. Radiation also impacts all of the optics, lasers, but even just glass will start to get gray. Due to also defects, it still works, but it starts to get sort of dark cylinders. It literally turns gray and loses quality, right, or transmission. Okay, so this was sort of the main topics I wanted to cover, and what I have now is a few more slides on Outlook. Of where I think this this might go in the future. But before I do that, any more questions on sort of the implementation or the technology right now? Okay, so for quantum networks in space, I think there's going to be a lot of different topics that have to be worked on, and you know, ultimately we want global networks and global, I guess, ultimately a quantum internet, right? And satellites is one way to bridge the large distance gap of this. And so this is a picture from a sort of a review this was from the Chinese academy, where they outlined a little bit about the future prospects for satellites, and I think they had a really nice picture which sums up the problem of satellite QKD. So I talked a little bit already about the different orbits, and unfortunately this picture became grainy when I copied it into PowerPoint. But the basic idea is the following, right? We have the Earth and the Sun. And so our primary problem with doing QKD is background light, right? So we have to make sure we can operate without too many background signals. And when we have a low Earth orbit satellite, the ones that I discussed, you know, like a few hundred kilometers high, only above the ground. So they're circling the Earth relatively low. So there's a good section of this orbit where it's in the shade of the Sun, right? So it's it's shaded in the shade of the Earth, so it's shaded from the Sun. And so one can do QKD down here. But if I get a satellite at a higher altitude, the region of complete darkness actually gets less. And so ultimately, if I have a geosatellite, the chances that it's literally in the darkness of the Earth is actually a bit of a problem, right? And then I also have to think about my ground stations. Where are they going to be located? Are they going to be, can I reach, let's say I want to go, you know, from one side of the Earth to the other. Can I find a good combination where the two ground stations are both in the darkness at the same time or not, right? So those are a few of the challenges, and in particular, right, there's a lot of background in the sky. These are this is the transmittance, and through the atmosphere, and this is the black body radiation. And there's a lot of solar radiation that we see in the sky, right? The sky is blue, so even if I don't get direct sunlight into my receiver, the signal still has to pass through the sky that has a lot of scattering, right? And it has a lot of brightness as well. So that's a real consideration and a real problem. And if I want to have a network of satellites, like multiple satellites around the Earth, they will most likely all be in the Sun, right? And so one has to deal with that. So that's definitely one of the sort of the future challenges. And the other point I want to make is that I think the ultimate sort of way forward will be connecting satellite links to quantum memory systems of some sort. So, like I mentioned, we've been part of this hyperspace project where we studied an all-photonic entanglement link between Canada and Europe. And just an all-photonic method, it can work, but it's very limited in terms of rates and possibilities. So ultimately, one will have to interface with memory systems. And there's already been multiple proposals for quantum repeaters using space segments and satellites, or memories in space even, right? And there's a lot of proposals around. And one direction is that I'm personally very interested in is, for example, to interface with quantum processors And I'm just referring to this paper here from the photonics company, which has silicon-based qubits, which nicely interface in a nice photonic wavelength. So they're quite well suited as a possible candidate for such a memory. But there's many other such memory systems that could maybe be used. And I'll just say that in Canada we've come up with a kind of proposal for a next generation mission which will do exactly that and interface the long distance satellite links with some kind of memory, and hopefully, it's a long shot proposal to maybe do teleportation across Canada, right, as a goal. Now that sounds like a bit, teleportation in itself is not too useful, but it does have a lot of elements of a proper quantum network, meaning one has to interface with memories, one has to do operations like entanglement swapping or this Bell state measurement and so on. So these will all feed into this quantum network of the future. As I also mentioned or briefly discussed, high altitude platforms, HAPS is a big topic that's coming up, where from a high altitude platform, which are, let's say, a stratospheric balloon or something flying above the weather, might also allow us to really bridge this long distance satellite link, but from above the weather, so that it just performs at a much better quality. And so there's proposals out there maybe to connect a high altitude platform with the satellite on one side and with the ground, and maybe even using a wavelength that is better suited for clouds going to the ground. So those are a few of the future directions that are in the works. Okay, and I think I'll leave it there. I wanted to leave it there, but I have like 100 more slides, so I can talk about any topic related to this. But I wanted to stop here. But of course, we're open for questions or discussions.
About those levitating optical devices.
The what, sorry?
Levitating optical devices.
Levitating optical devices.
Strasbourg University and all that, they work on this. The flying optical devices that helps for the infrastructure.
I'm not sure what that. Yeah, I'm not familiar with that, so I'm not sure what it is. I know that maybe you mean this macro there's a protocol macro, and there's some work on levitating sort of nanoparticles to study quantum physics in a fundamental regime. Is that what you mean?
No, it's.
But that's not QKD. They're trying to study. They want to make a satellite and levitate those particles in a satellite environment where there's not much, G-force, so that they can look at the quantum decoherence of a massive particle. But I'm not sure if that's what you meant.
I think it's.
But those ones, I don't think there's a connection to QKD for those systems. But still, it's another fundamental quantum system that benefits from the space environment. I will say, maybe I don't have a slide for that, or pictures, but there's also commercial activity for satellite QKD. What I showed you at those missions, the Chinese one, but also the Canadian one that we're working on, those are more sort of scientific or research platforms. Those satellites are relatively big, the payloads are relatively big, and there's a couple of commercial endeavors now for building commercial satellite QKD with much more compact solutions, right? Because they have to be smaller and really optimized for QKD rather than, let's say, quantum science. And that is also happening. So in Waterloo, in Canada, we have a startup, it's called Keynet. And so this whole satellite payload was downsized to a small unit which has everything inside, detectors and recording, data acquisition, into a small item which has like, I should say a small system, which has on the order of 2 kilograms mass, and it's not so big, low power. So the idea is that it can be integrated onto a bigger satellite. Let's say there's a large telecom satellite or Earth observation, and it could just be added on as a piggyback and used by the satellite provider for example, for rekeying the satellite. And the other one, and of course there's objectives to build a QKD network for ground users and ground users in different cities. But those commercial systems now are looking to bring the price point down a lot, right? Where the cost of a unit can be really reduced, and hopefully that will also help enable this technology to expand, right? Because to date, QKD, and in particular satellite QKD, is still rather on the research side, even though there's commercial entities, but it's still more considered a research endeavor. There's also a company in Singapore, and they're also working on commercial satellite QKD satellite missions. And if it goes well, in a year or two, some of those commercial satellites will, so commercial QKD satellites will have been demonstrated. So keep a lookout for that, because hopefully that will also help, move this whole field forward and show that it is viable to use those systems. A big problem with satellite QKD is side channels. I didn't talk about that at all. And the problem is that we have the channel is open, right? If you think about it, it's not like a fiber where if one wants to get to the fiber for hacks and attacks, one has to dig up the fiber somehow or access it. If you think about it, the satellite is just looking, facing the ground, and technically it's a bit, open, right? It's just looking down. So that can lead to some side channels, right? So one has to deal with those problems of, in particular for commercial QKD system, of how to deal with all the various side channels. I'll give you a simple example. Photon detectors have a backflash. Avalanche photodiodes, when the photon goes in, there's an avalanche that creates a macroscopic current that can be measured. So it's an easy, great easy method to detect single photons. However, this large current avalanche creates photons. And if you have two photon detectors looking at each other, they will keep sending photons from one to the other, so they could just, start triggering at each other. And yeah, we have measured that and we see it. Various of those detector technologies show that. So hypothetically, you could have a QKD system in space or on ground, and if you just look down, you could catch that backflash and see which detector fired, right? So there's been hacks on, hacks, or I should say studies on that hack. And they have shown indeed, with a regular quantum receiver, you do see the photons coming out, propagating backwards through your polarizer, so they nicely have the polarization information you want. That's just one example of a hack. So, and those, on that front, there's still a lot of development. So those commercial QKD systems from those companies that I mentioned, they are trying to, in particular, work on that. So rather than just showing the basic science, now they have to think about all of those back doors and side channels and whatnot. So that adds a lot of actually complexity when testing and implementing the systems. So, okay, yeah. Any more questions right now or discussions? Okay, well, thanks a lot. I hope I was able to give you an idea roughly how QKD with satellites works and how it's implemented and all of the major issues and questions around that. And thank you.